Hello, Dr. Mears and fellow classmates who will be watching this video presentation. My name is Matthew Simonar, and I'm a senior studying mechanical engineering.
My name is Andrew Stalheim, also a senior in mechanical engineering.
So we decided to do our report on the thermodynamics of internal combustion engines, more specifically three configurations that are tested and specifically documented in this paper. IC engines are commonly found in everyday life and are very well documented because of low cost, high power density, reasonable efficiencies. They correspond to most emission standards nowadays, and they run readily off fossil fuels we have available to us. As of now, they can provide us with continual operation with minimum needs to refuel. And the main goal with IC engines in the future is to increase thermal efficiency and get a performance boost. Within this paper, you'll find three examples on IC engines, one being a low heat rejection system, an exhaust gas dilution system, and an ideal Otto cycle.
So to begin with, we'll just do a quick overview of the laws of thermodynamics, being each the first and second law. The first law, it describes how work and heat transfer are different forms of the same energy, the same quantity, and can be transferred between. Um, Energy remains constant, but can change form to, say, a mechanical output in the case of an engine. And for a control volume, for example, a piston cylinder device, the change in energy has to be equal to the inputs and the outputs. The second law of thermodynamics was first brought about by Carnot, leading to the Carnot cycle. Um, it'll be used to determine the direction of the process, establish conditions of equilibrium, specify maximum possible performance of the thermal system, and identify aspects that will be detrimental to the overall process. Common statements are used to describe the second law is the Kelvin-Planck and Clausius statement. And an additional feature of the second law is it quantifies the quality of energy through the concept of exergy.
So our first example is not really one of the three, but it was just a general IC engine cycle simulation overall, and it was a four-stroke, three-zone process of just a basic IC engine. To complete this test, really, you need multiple empirical submodels. It's not exactly easy to do, but in figure one to the right, you can see that the black dash lines indicate the control volume being examined, with arrows in and out indicating your heat transfer in and your work out. Uh, to find these empirical submodels, you need multiple properties, and the working fluid of the engine is believed to obey the ideal gas model. So the unburned mixture during compression is a mixture of air, fuel vapor, exhaust gas, recirculation, and residual gases. And burn gases from the engine are determined by stoichiometry and equilibrium composition. Some of the properties are the kinematics, such as the cylinder bore, the stroke, the connecting rod length, compression ratio. And to use these, you can determine instantaneous cylinder volume and surface area. Combustion is found from equation one to the right. XB is your mass fraction of fuel burned. A and M are constants given, and Y is calculated from your crank angle, your theta O, which is your start of combustion, and your theta B, which is the duration of your combustion. Heat transfer is found using equation 3, where A is a cylinder surface area, H is your heat transfer coefficient, and T is the temperature values in the engine. Mass flow rate is determined from one-dimensional flow, and mechanical friction is from rubbing, whether that is on the crankshaft, the bearings, pistons, or the valve train, and from pumping, auxiliaries such as the oil and water pumps or the alternators. The simulation was done with a 5.7 liter V8 engine, properties listed to the right. I'm not going to go through them all. They're there if you need them. The values of the simulation that were done are seen in table 2 right below that, using 2000 RPM, a brake mean effective pressure of 900 kilopascals, a compression ratio of 10, and a burn duration of 50 degrees CA. The fuel used was isooctane, and really a large part of IC engines is the exergy destruction, which is great when it relates to this class. And it's determined from the same equation that was defined in class, where U being specific energy, V specific volume, and S being specific entropy. The O values are obviously determined at the dead state, as we found out. And the last two equations, equation 5 and 6, in 5, you find the exergy of the fuel for the model, which is found using Gibbs free energy, and the exergy destroyed is by finding a percentage of fuel exergy. So the results of the tests are shown in figure 2. I'm not going to spend too much time just reading percentages off to you guys. So it's just important to note that exergy during the combustion process is highly irreversible due to chemical reactions, heat transfer, and mixing associated with combustion. But extensive research has shown sort of unique results that directly come from the second law of thermodynamics is the quantification of exergy destruction during combustion directly correlates with the temperature of combustion. And in certain conditions with higher combustion temperatures, more fuel exergy is preserved, and with lower combustion temperatures, less fuel exergy is preserved.
So the first model that I'll be discussing is the low heat rejection model. In this case, we typically see a large heat loss through the cylinder wall, the head, and the piston that result in a lower efficiency in a typical IC engine. So the idea with the low heat rejection engine is that you're going to attempt to move towards an adiabatic condition where the heat loss is brought closer to zero during operation. Um, to achieve this, we typically see a low conductivity material, such as a ceramic, used to reduce the heat transfer out of the cylinder during operation. But that typically comes with another concern of durability, where the ceramic can't hold up to the typical operation that we see. Another advantage is that you'd be able to remove the cooling pump, which would reduce the engine load, therefore increasing efficiency of the engine. And the last advantage of this would be the higher EGT, which would result in a higher efficiency of your turbo, just due to the temperature differential between the inlet and outlet on the turbine side of the turbo. So looking at figure 3, we see that we're using 450 as the wall temp for a typical IC engine, which we'd see today, and moving all the way up to 1500 Kelvin, which we're going to assume is approximately the average temperature inside the cylinder. And therefore, there's not going to be a net heat transfer in or out of the cylinder during operation. So even though the net transfer is zero, figure 4 shows that there is an instantaneous transfer, being that on the intake and compression, there's energy transferred from the cylinder wall to the exhaust gas, or the gases inside the cylinder, rather, and then vice versa on the combustion and exhaust. So the brake mean effective pressure is held constant at 900 kPa between both the 450 and the 1500 Kelvin simulations. And from this, we can see that the pressure inside the cylinder is increased through the increase in temperature, and therefore results in increased compression work, but also increased expansion work. So the results in net efficiency are more seen in the thermal efficiency rather than the compression and expansion. Low heat rejection engines typically have a lower gamma, which would result to there being less thermal energy converted into work. We'll discuss that a little bit further in the presentation. So as the wall temperature increases, the work only increased by about 1.5% relative to the heat transfer decrease of about 16%, which you can see in figure 5. Um, so reasons for this might include looking at the available work through the heat transfer, which you can see in figure 6, exergy, where only 13% is available for mechanical work versus the 16% of energy that's available to be reclaimed through increasing the wall temperature. The average gas temperature is increased, as I mentioned before, but due to this, the volumetric efficiency of the engine is decreased slightly just because there's less mass coming into the engine. The decreased gamma could also result to this, as well as the increase in EGT, which will account for a significant portion of that energy. So in figure 5, you can see that about 43% of the energy is put out through the exhaust gas, while at 1500 Kelvin, it moves all the way up to about 58%. And that's just due to the increase in temperature through the exhaust gas. Another assumption that was made is that you could maintain a 1500 degree Kelvin wall temperature, but In the real world, we know that it's probably not possible, and therefore you might move to something like 800 Kelvin, where your increase in efficiency is minimal, going up by about 0.5% in energy output.
So our second example we have is an engine that was tested using EGR, or more commonly known as exhaust gas recirculation. And this method basically takes nitrogen oxide emissions, and it's a technique used in most gasoline and diesel engines. And you recirculate a portion of the engine's exhaust gas back into the cylinders of the engine by essentially using external piping, which just redirects the exhaust gases into the inlet stream. So there's more cooling for the recirculated gases. This method alters the thermodynamic properties of working fluids in the engine, causing concentrations of the inlet to change. And it also causes a decrease in the combustion temperatures, which both of these changes directly affect the ratio of specific heats and thermal efficiencies. Um, the test results for this method are shown on the two next slides, while the test conditions are shown directly below in table 3. All the plots are shown with the percentage of EGR on the x-axis and their respective tested variables on the y-axis. Figure 7 is exergy destroyed, figure 8 is heat transfer percentage, and figure 9 is thermal efficiencies. Those are all on the y-axis. So the first plot, or figure 7, shows that an engine with a diluted exhaust gases, there's an increase in exergy destroyed, and the engine with the adiabatic EGR has lower exergy destruction, and this is just due to the fact that there is a temperature decrease from the cooling of the gases. So with lower temperature, there's more exergy destroyed. The second plot, figure 8, shows that with a cooled system, the amount of heat transfer is decreasing because the temperature of the gas is decreasing. And with the adiabatic EGR system, there's more heat transfer because the temperature of the gas is obviously increasing. In the final figure, figure 9, the increase in EGR, the brake efficiency and overall net indicated efficiency increase over percentage increase of EGR, while the adiabatic test engine shows decreases in both brake and thermal efficiency. So a system using a cooled EGR, it simply shows improved performance results and higher work output compared to the other two systems. The one system being the adiabatic test and the other being no EGR at all, just your basic IC engine. The cooled system with EGR shows the lowest heat transfer, the highest amount of combustion, and the lowest amount of net transfer out due to flows.
So next I'll be discussing the Otto cycle, which is one of several ideal air standard models used or available. The Otto cycle is typically used to model IC engines and is based on a constant volume heat addition process to replace the combustion process. A couple assumptions that are made for the Otto cycle is that the working fluid is air, the compression and expansion process are adiabatic and reversible. The combustion process is replaced by a heat addition process. The exhaust blowdown process is replaced by isobaric heat rejection at bottom dead center. And the intake and exhaust strokes are neglected in this model. So making those assumptions will allow us to calculate a efficiency of the engine. And what's found is that this efficiency is typically inconsistent with the actual IC engines. So some pieces of the Otto cycle that are consistent with typical engines is the compression and expansion process, the temperature increase due to thermal energy addition, and mechanical conversion of pressure to work. However, we can see that, or talk about the inconsistencies with the actual engine, starting with the fact that it's using the heat addition process rather than a chemical conversion. So in a chemical conversion, you'll typically see an irreversibility, which you won't necessarily be able to model by just utilizing the heat addition, which the Otto cycle assumes. As I had mentioned before, there's heat transfer out of the cylinder, which the Otto cycle doesn't necessarily account for. The combustion process in the Otto cycle occurs at top dead center, whereas in an actual IC engine, you'd see that across a wider range of crank angle degrees. And then just some other things, the blow-by, incomplete combustion, chemical disassociation, and mechanical and fluid frictions aren't accounted for either. So figure 11 shows a PV diagram of the Otto cycle with each the isentropic compression, expansion, isobaric, heat addition, and rejection. And then moving to figure 12, we're looking at gamma here and the effects of gamma on the compression work and expansion work. So this is relating back to kind of what we talked about before, where decreasing gamma, which is the specific heat ratios, is going to change or alter the efficiency of the engine. And then each of the calculations for compression work and expansion work are shown in figure 7 and 8 respectively. And we assumed a constant compression ratio of 16:1 for that. So decreasing the gamma is going to help us in increasing the efficiency because the ratio of compression to expansion work narrows, which is beneficial. As well, it's also worth mentioning the compression ratio is going to have an effect, and increasing the compression ratio is typically going to have a positive effect on the efficiency of the engine. So just to recap, first talked about the thermal laws and how they were kind of used, and we showed how they were used through a couple examples there. The importance of gamma, where having a increase in gamma is going to yield a better um, thermal to energy, thermal energy to mechanical energy conversion. And then the low heat rejection engine, which increase the wall temperature, decrease the heat loss, and increase the thermal efficiency. But we saw that there was little efficiency gained by utilizing this. There are some obstacles in doing so, including the materials there, where typically we'd want to use a ceramic, but couldn't because of the durability. And then we saw that if you were able to increase that wall temperature, you'd typically be able to get a little better efficiency out of your turbo.
Uh, and the second example, we saw that exhaust gas dilution or recirculation basically just recirculates gases from the engine to improve thermal efficiency overall and reduce your heat transfer into the engine. Um, the cooled exhaust gas recirculation provides lower heat transfer and a higher thermal efficiency compared to your standard IC engine, while the adiabatic EGR shows a higher heat transfer and lower thermal efficiency than cooling and running it through that circulation cycle.
And then last, we talked about the Otto cycle, which um, modeled the engine as a heat engine rather than a chemical conversion device. And while there are some things that the Otto cycle models fairly well, as far as internal combustion engine, um, it does neglect some combustion and irreversibilities and isn't necessarily 100% accurate to what we'd like to see. Um, but one thing it does do well is it shows us the effects of gamma and the compression ratio on the efficiency of the engine. So then with that, if there's any questions, please let us know. Thank you.
Thank you.